Okay, now I've defined a new function on trees, and this function will take a tree and return the number of elements in it. And I've called that function size. So here's the function. Size takes a tree with any type in it and returns an int that represents the number of things in that tree. How is it defined? The size of the null tree is 0. I guess that makes sense. An empty tree's got nothing in it. And the size of a tree with stuff in it, node x, t1, t2, is 1 plus size t1 plus size t2. So the size of a tree is at least 1 because here's something in it, x is in it. So it's 1 for x plus the size of the left-hand subtree plus the size of the right-hand subtree. So size is defined recursively. Okay? And we've got the rev function from last time. We'd like to prove that for any tree t, if you reverse the tree and take the size of it, it's the same as taking the size of the original tree. So this is basically saying the size of a tree does not change if you reverse it. We'd like to prove that using induction on trees. Okay? So the first thing I have to do is I have to prove the base case. I have to prove base case. And the base case is when the tree T1 is null. Okay? So what do I have to prove? I have to prove that the size of rev T null is equal to size null. Size of rev T null is equal to size null. Okay, so we'll start on the left-hand side like we usually do. So we're computing the size of the reversal of the null tree. What's the reversal of the null tree? Let's have a look at the definition. Rev T null is equal to null. So we can replace this with size null by rule T1. Okay, and what's the size of the null tree? It's empty. Sorry, it's 0 by definition using rule S1. 0 by S1. Okay. Oh, I'm sorry, we're done immediately. I didn't even need to do that step. Size rev null is size null by T1. So we're done immediately because that's equal to the right-hand side. Okay, I didn't even need to go that far. So it's only a one-liner. So it's proven for the base case. Now we're going to prove it for the step case. Okay, so step case. Again, let's have a look at the definition of induction on trees. I've got two inductive hypotheses here. So to assume that the property holds for T1 and T2. Okay, so we're going to assume that size rev T T1 is equal to T1. I'll call this my first inductive hypothesis, IH1. I need to assume that size rev T T2 is equal to T2. And this will be my second inductive hypothesis. I call it IH2. Those are the two things I'm assuming. What I've got to prove, I have to prove that the size of the reversal of a tree built out of these two things, node A T1 T2, is the same as the size of this tree here, node A T1 T2. I have to prove this for any new element A. All right. So we let A be arbitrary, arb for short, and then we start with the left-hand side like we usually do, which is size rev T node A T1 T2. Okay, what is this equal to? Well, let's have a look at the definition of reversal. Reversal of a tree is you leave the element alone and then you swap the two subtrees. So we'll do that. This becomes size of node A T2 comes over here, rev T T2, and T1 goes over there, rev T T1. All right. What rule said I could do that? T2 said I could do that. What's next? Well, now I can apply the definition of size. So the size of a tree, if it's not the null tree, is 1 plus the size of the children. So we have 1 plus size of rev T T2 plus size of rev T T1. What rule said I could do that? The definition of size, S2. Okay? Now I want to somehow get to this term here. If we expand out this term, I'll get size T1 plus size T2, which doesn't quite look like this. So we have to get rid of these annoying reverses. Thankfully we can do that using our induction hypotheses. So we apply those. So size of rev T2 is just size of T2, size T2, plus size rev T1 becomes size T1, size T1. by the inductive hypothesis 1 and the inductive hypothesis 2. Okay? Now, this term here almost looks like this term here. I just have to exchange these two terms. And thankfully I can do that because addition is commutative. Addition doesn't matter which order you do it, right? So this is the same as 1 plus size t1 plus size t2 by math. Maybe addition is associative if you want to be pedantic. And then I can apply S2 backwards to get this in the form I need. So by applying this rule here backwards, this term here is the same as this term here. So we have size of node A T1 T2, which is equal to the right hand side of the thing I wanted to prove. I almost forgot the rule. That was rule S2. Okay, proven for the base case. We assumed it to be true for two trees and proved it's true for a new tree built out of them with an arbitrary new element in the root node. So I proved it for the step case. Therefore, we've proven this statement here for all trees T.